So I got a request from one of the subscribers to do Laplace transforms, and since I don't know what your level of experience is with them, I'm going to assume no knowledge about Laplace transforms. So when you're dealing with circuit analysis, you're dealing with sinusoidals for the most part, and one of the great things about Laplace transforms is that it takes functions from the time domain and puts it into the frequency domain. And the great thing about the frequency domain is once we have transformed the time domain into its frequency domain equivalence, a lot of the techniques in DC circuits will also apply to the AC circuits in the frequency domain, and that is extremely super duper cool, because without Laplace transforms, what would happen is that we would actually end up having to do, in order to solve any circuit, we would have to do solve simultaneous systems of partial differential equations, which is really, really difficult math. And of course, if you have done analyzed DC circuits, you know that that's pretty much linear algebra. And linear algebra is far easier than partial differential equations, so Laplace transforms are awesome for that reason. And so if you're learning about Laplace transform, then you must have learned about phasors. There is a lot of analogies. When we first dealt with the time domain, we found that, you know, when we started doing the analysis, that it got pretty complicated. We had first order differential equations. So then we converted the equations or the components, circuit elements, into phasors, and the analysis got much easier. Laplace transforms are pretty much the same thing. So what a Laplace transform is, L of f of t, is you take some function in the time domain, like cosines. In our case, since we're electrical engineers, we're taking sinusoids, which are a function of time, and we're transforming it into the frequency domain. And that is going to be, we're going to call that f of s, and that's going to be the function, the integral of f of t times e to the negative st dt. So that is the definition of a Laplace transform, and again, that's just mathematics. What technically we're doing is we're taking it out, we're putting it into a domain where DC circuit analysis techniques apply, and that is super duper cool. Now, before we do that, we have to be able to, as engineers, be able to look at certain functions and be able to say, okay, I can represent this function by this formula, because before you can even do a transform, you have to be able to express a given function as in the time domain. So one of the most common functions that we use in engineering is the step function. The step function models things such as switching. At a certain time, you're at time 0, and at another time, you're at time on, or you got time off. So that's the unit function, or which is a subcategory of the step function. So in the Nillson book, there is a problem, since my YouTube channel is largely for people who are going to college and are using certain popular textbooks, so that they can, if they get stuck, then they can unstick themselves. That's the purpose of my channel. But the book, the appropriate chapter that is Laplace transform in the Nillson book is chapter 12, and I'm going to take from that problem number 2. And today's objective for today's lesson is to take a simple function that you would see in everyday engineering, and then be able to write the f of t, because without the f of t you can't do any transforms, so you have to have that level of skill. So this is a step function that they gave us in problem 2, step A, and it's a pretty simple one. It's a line of slope 1, slope positive 1, and slope negative 1 this way. And at time negative 10, before time negative 10, we're at 0, and then there's slope 1 all the way to time 0, and then from time 0 to time 10 seconds, then after time 10 seconds, and the function turns off. So the way we express that as f of t is f of t is equal to the sum of this function from here to here to this function. So it's going to be some u of t. So it's going to be negative from here to here, the slope is 1, and the y-intercept is 10. So it's going to be t times u of t minus a negative 10, so you subtract from the beginning point of time, so that becomes a minus and a minus is a positive, so u plus 10 minus, and then over here you have u of t plus 0, because you're at time 0. We're adding and subtracting. Basically, we're saying this u is a function of this time subtracted before. You subtract all the time before time negative 10 units because the function doesn't start until there, and then it stops. So you subtract from here the rest of the time, which is at time 0. That's one piece of it. So we have described this function from here, from negative infinity to time 0. Now we need to describe it from time 0 to positive infinity. So it's going to be plus the second part of this function, which is going to be negative 10, right? Negative t, we have a negative slope here. So plus negative 1t times u of, and then we want to start here. So it's going to be u of t minus 0, because we want to subtract all of this away from it. And that's going to be minus u of t minus 10. Okay. So what we want to do is we want to combine like terms. So distribute everything through. That's going to give me t u of t plus 10 minus t u t. T plus 0 is t. That's going to be plus a negative, so this is going to be minus t u of t. And then a minus, and a minus is a positive, so plus t u t minus 10. Okay, so now we can combine some terms. These two come together, and that is actually all that combines. So the final expression for this term is t u t plus 10 minus 2 t u of t plus t u t minus 10. And that's the final answer for that. Okay, so I'll do some more problems next time. Actually, the next part B, is actually pretty long. So I will get you guys started on that one, but, well, I guess I can finish it. So that's how you express a step function as an f of t, and that is the prerequisite step before you can actually do any kind of transform. So the next part B, is, for part B, they have this function. We have here at negative 9, up here is actually, sorry about that. So we have a function that looks like this. Crosses up here. We have negative 3, negative, oops. This is negative 2, negative 1, negative 8. This is positive 8. 1, 2, and 3. So pull back on your experience with algebra. You know how to compute the slope here, rise over run. So this is going to be your rise. The slope in this section will be -8, and it's going to be, and then the run is 1, and this is, so the slope here is going to be -8, right? So this slope is -8, and the equation here is if you continue down here, you're going to end up at the y-intercept. Actually, let's build a table. So from the interval -3 to -2, we want an interval from -2 to -1, -1 to 0, oops, from -1 to 1, and then from 1 to 2, and then from 2 to 3. So we have those intervals, and what we want to do is we want to find the equation that describes it. So here you can see your rise is 8, and your run is 1, so your slope is going to be -8 because it's slanted this way. So m is equal to -8, and if you continue down there, your y-intercept is going to be -24. So that takes care of that piece. And then what you're going to do is you're going to subtract everything from time here, everything from time here to describe that piece of the piecewise function. So over here, we have slope 0 because it's a horizontal line, and the y-intercept will be -8. So what this piece of the function is described as basically y is equal to -8. Again, subtract everything here, subtract everything here to describe it. From here to here, you see your rise is going to be 16. It's going to be a positive slope because we're angled this way, and your run is going to be from -1 to, it's going to be a distance of 2, so it's got to be 16 divided by 2, which is 8. Positive 8, and your y-intercept is right there, 0. So this slope is described as y is equal to 8x. Okay. And from 1 to 2, slope is 0, and so y-intercept is 8. The equation that's going to describe that is y is equal to positive 8. And from here to here, we have y-intercept will be, well, first of all, the slope is going to be, rise is 8, from 0 to 8. That's your rise. And then from here, your run is 1, so your slope is, your angle this way, your slope is -8. So your m is -8. Your y-intercept, if you continue, is going to be 24. So, now is the part that's actually not fun, but we can do it. It's just basic algebra, which is kind of a pain in the neck. So we have to describe our f of t, which is our function before in the time domain, our step function in the time domain. To describe such a step function, we take a look at each interval and subtract the time before from the time after. So here, our first equation we had was y is equal to -8x minus 24. Okay, so that gives us, that tells us, it actually should be really t. So we have -8t minus 24 times u of negative times a negative is a positive, so u plus u of t plus 3 minus u of t plus 2. That's that first piece. So now we've described that piece of our original function. We go to the next piece. Now we describe the interval from -2 to -1, and that was -8. -8 times u of t plus 2, because it's really t minus -2. We're subtracting everything before time -2, and then subtracting everything after time -1. So that's going to be minus u of t minus of a negative is a positive plus 1. And from that, we are going to handle the interval from -1 to 1, and that interval is described by y is equal to 8x, or 8t times u of t minus -1, which is t plus 1, and then t minus u of t minus 1. Okay, so now we've handled that interval, and now we need to handle the interval from time 1 to time 2. So that's going described by the equation y is equal to 8. That's a horizontal line. So that gives us y is equal to 8 times u of t minus time 1 minus u of t minus time at 2 seconds, or 2, whatever the units. And the last interval is from 2 to 3. So that gives us, and that equation was described by y is equal to 8t plus 24. So we have 8t plus 24 times u of t minus 2 minus u of t minus 3. So that is the piecewise function that describes the original function that we saw. And so that describes this in the time domain before we Laplace transform it. We can simplify this. In fact, I believe the book wants you to simplify that. And it's really simple. It's just you're going to combine like terms. So we have negative 8t minus 24 times u of t plus 3. Distribute that through. That gives me minus and a minus is a positive, so that gives me plus 8t plus 24 times u of t plus 2. Next term, this gives me minus 8 u of t plus 2. Minus and a minus is a positive, gives me plus u of t plus 8u of t. Plus 8u of t plus 1. Down here we have plus 8t times u of t plus 1 minus u of t minus 1 minus 8. 8t minus 8t u of t minus 1, next term, plus 8 u of t minus 1 minus 8 u of t minus 2, last term, is, we have 8t plus 24 u t minus 2 minus 8t plus 24 times u t minus 3. So now you can tell why I wasn't really excited about doing that, because we're engineers, we're not math people, and this was kind of a pain in the neck. So, but we still need to be able to express any given step function algebraically in order to transform it. Can't transform something that's just a wave. We've got to give the wave a time domain expression. So we can start combining like terms. U of t, do I have any other u of t, t plus 3? No. So this is just by itself. We're going to rewrite this as negative 8t minus 3 u of t plus 3. Next, u of t plus 2. So now I'm done with this. Next, do I have anything else as t plus 2? The t plus 2, I have a t plus 2 here. And that is it. So that gives me, I'm going to factor the 8t, and we're going to call that, actually I'm going to put it on the line below, plus 8, factor out an 8, we have t plus 3, u of, since we have a t plus 2, we can combine these together. So 8 actually, this should be, so this is a coefficient, this is a coefficient, so we can combine the coefficient. So we have 8t plus 24 minus 8. Combining this coefficient with this coefficient because the u of t of 2 is the same thing. So that gives me u of t plus 2. Now I'm done handling that term. Looking for t plus 1, and I have a t plus 1 here. Step functions are symmetric, so that's how they play out because you're subtracting time and they'll go in a progression. So I can combine the coefficient here, which is 8, with the coefficient here, which is 8t. That gives me 8t plus 8 times u of t plus 1. Done, done. Now we have a t minus 1 and a t minus 1 here, and the coefficient of t minus 1 is minus 8t, positive 8. So we have plus minus 8t and positive 8. That's times u of t minus 1. Done and done. Next we have t minus 2 and a t minus 2 right here, just like I expected. So the coefficient there is minus 8 and 8t plus 24. So we have 8t plus, whoops, sorry, I'll go in order. Minus 8 plus 8t plus 24. That's going to be times u of t minus 2. Done and done. And then the last term doesn't combine with anything. It's just all by its lonesome. Last term is 8t plus 24 u of t minus 3. Okay, so now we can simplify that to a final t equation. That is equal to negative 8 times t minus 3 u of t plus 3 plus negative this gives me 8t minus 16, right? Because, oh, excuse me, plus 16. So that's really plus 16. I can factor out an 8. That gives me t plus 2. U of t plus 2. And then here, we're going to factor out an 8 plus 8t plus 1 u of t plus 1. Then here, we're going to factor out a negative 1 minus negative 8. We're going to factor out negative 8. That leaves behind a t minus 1 times u of t minus 1. And here, this and this, negative 8 plus 24 is positive 16. And I have a sign error somewhere because this is a symmetric function. So this should be 8 times t minus 2 times u of t minus 2. And then here, the last one, and I have a sign error somewhere, and this should be minus 8 times t minus 3 u of t minus 3. And this is how you express this step function in the time domain. Okay. Negative 3, negative 8, 8, 2, negative 2, negative 1, 1, 2, 3. Okay? All right. I know that seemed boring, but it is a fundamental skill that you need. Next week, we'll actually do some transforms. We'll do the impulse. We'll talk about the impulse function. And then after the impulse function, we'll do talk about the differences between functional transforms and operational transforms. And there are tables so that we don't have to derive every single typical transform that we'll encounter. We'll use those tables rather than doing it every single time because we'll run into those typical functions quite a bit, and then we'll take some AC circuits and transform them and use DC techniques to do circuit analysis with it. Okay? See you next week.